alaikum wa rahmatullahi wa barakatuh. Hi everyone, nice to meet you all. Today inshallah we will start together in new topic in organic chemistry. Today inshallah we will start together in isomerism. At first, it is one of the important topics in organic chemistry. We will separate our topic today into two videos. The first video for structural isomerism and the second video for stereoisomerism. At first, let's start together with isomerism in organic compounds. At first, we will explain isomerism in organic compounds is like isomerism in humans. What is the meaning of isomerism in humans? In humans, we start with growing. We are growing from small baby and we are changing into small boy in primary. Then we are boys in secondary schools. Then we are growing and we are colleagues. Then we finish our college and we start to work. Even in our work, we are growing. We are changing in positions from small worker up to the head of department, up to the head of our company, according to our ability. Then, after retarding, we are converting into old men and old women. So, we are changing in our daily life. We are changing from one position to another position. It is exactly like organic compounds. Organic compounds are the same. We have different shapes of organic compounds. We have different structure of organic compounds. We have different functions of organic compounds. Exactly, even if we are in any one of our growing stages, we have different types of behaviors. We have different types of acting. Sometimes we are happy, sometimes we are angry, sometimes we are in love, sometimes we feel with hate. So we are growing, we are changing every time. So, changing in humans is exactly like changing in organic compounds, in isomerism. So, let's start in our organic compounds in different types of isomerism. At first, in isomerism is the property of two or more compounds. It is a property of two or more isomers that have the same molecular formula. Exactly, we have the same components. Exactly, we have the same molecular formula. Even if I am Riham, I will stay Riham forever. But in sometimes I was child. Sometimes I was growing. Sometimes I am a woman. Okay? So we are growing, we are changing. But exactly we are the same person. Organic compounds, isomers, are exactly the same compounds. They have the same molecular formula. But they are different in their structural formula. They are different in their arrangement. They are different in their behavior. They are different in their way of acting. So they are different in their arrangement of atoms. Just arrangement of atoms. So what's the different types of isomerism? Let's start to know different types of isomerism. At first, we have the first type of isomerism, structural isomerism. Inside the first type of isomerism, we have different stages. We have different another types. Like what? Like at first, we have a chain isomerism. Second, we have positional isomerism, and also we have functional isomerism. So, structural isomerism is separated into three main types. At first, chain isomerism, positional isomerism, and functional isomerism. The second type of isomerism is stereoisomerism. Stereoisomerism is separated into two main types. The first one is geometrical isomerism, and the second one is optical isomerism. Today, inshallah, we will start to finish just the first type of isomerism, structural isomerism. Structural isomerism is like growing in different stages. So we will start to explain our different stages in details. At first, let's start with the structural isomerism. First type is chain isomerism. In chain isomerism, we have isomers. Isomers exactly have the same molecular formula, but they are different in what? They are different in the length of the carbon parent chain. They are different in the length of our carbon chain. They are different in their lengths in growing, like us at first increasing in our length. The same in organic compounds, we have isomers. Exactly, they have the same molecular formula, but they are different in the length of our carbon chain. Like what? Let's start to have some examples to understand more and more. At first, we have butane. Butane is alkane. General molecular formula of alkanes is CnH, 2n plus 2. So we are talking about butane, CnH2n plus 2. 2. How many carbon atoms in butane? Meth, eth, prop, but. So we have 4 carbon atoms. So we are talking about general molecular formula C4H, 2 times 4 equal 8, 8 plus 2 equal 10. So we have C4H10. It is the structural formula of butane. So, at first, all of our compounds in butane, molecular formula is 4H10. What is about the structural formula? What is about the length of our carbon chain? At first, we have normal butane. Normal butane, we have its skeletal structure. We explained before in the skeletal structure, we just show our carbon atoms like small dot. So our carbon atoms is small dots. And we can't draw any hydrogen atoms. So we have 1, 2, 3, 4. We have 4 carbon atoms. It is the skeletal formula of butane. Our structural formula of butane, we have our stem, we have our parent chain. Our parent chain consists of 4 carbon atoms. 1, 2, 3, 4. It is butane. Second one, it's isomer. It's isomer. It's another shape. Is isobutane. 2-methyl propane. Our parent chain, our carbon chain length is changed from 4 carbon atoms into 1, 2, 3 carbon atoms. So our parent chain length is changed from 4 to 3 carbon atoms. So we change the length of our carbon chain, but we still have the same molecular formula. 1, 2, 3, 4. We have 4 carbon atoms. How many hydrogen atoms? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have C4H10. So exactly we have the same molecular formula, C4H10, but we are different in the length of our carbon chain. Second type of our chain isomerism, we have another example in pentane. Pentane, we are talking about 5 carbon atoms, meth, eth, prop, but, pent. So we have C5, H12, C5H12, all of our different shapes of our compound have the same molecular formula, C5H12. So all of them have C5H12, but they are different in the length of our carbon chain. So at first we have in pentane. Our carbon parent chain is C5. 1, 2, 3, 4, 5. Our skeletal formula, we say that we will represent each carbon atom as small dot. 1, 2, 3, 4, 5. So our chain consists of 5 carbon atoms. The second one is isopentane or 2-methyl-butane. Let's start to look to our carbon parent chain. We have 1, 2, 3, 4. It is the structure of butane carbon chain. And we have one branch. We have another carbon atoms. So at all, our general molecular formula is C5H12. 1, 2, 3, 4, 5. So it is C5. Hydrogen atoms 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So exactly we have the same molecular formula. The third one, 1, 2, 3. So our carbon chain changed from the 5 carbon atoms into 4 carbon atoms into 3 carbon atoms. So the length of our carbon chain, our parent chain, is changed, but we still have the same molecular formula. So we have different isomers. So we can say in 2 and 2 dimethylpropane, we have 1, 2, 3. It is our parent chain. It is our carbon parent chain. And we have 2 branches, CH3, CH3. So we have 2 different branches attached to our carbon chain. So it is the first type of isomers, chain isomerism. Let's transfer to another type of isomerism. We have positional isomerism. If I am working in any place, if I am working hard, I will change in my position. But even at the beginning and at the end, I am the same person. So we are growing in our positions. Exactly in our organic compounds, compound have the same molecular formula. We understand what's the meaning of molecular formula, but they are different in the position of their substitution or in the position of our functional groups. So positional isomerism, isomers have the same molecular formula, have the same carbon chain length, but they are different in the position of our substitution of our functional group. But we are different in the position of our functional group or substitution. Let's start to have some examples. We have different types of alcohols. We have different names of alcohols. They are just different in the position of our functional group, hydroxy group. In the first one, we have our hydroxy group in position 3. So we have 3-meth-prop-but-pent, 3-pentanol, or we can say pentan-3-ol, as the position of hydroxy group is different. In the second one, our functional group, our hydroxy group, in position 2. So we have meth-eth-prop-but-pen, pentan-2-ol. But in our last isomer, we have our functional group in position 1. So we have pentan-1-ol. So we have different compounds. All of them have the same molecular formula, but they are different in their position of the functional group. We are different in the position of hydroxy group. So we have different types of our isomer. Okay, but all of them are positional isomers. Another example, in our compound we have substitution. We have guest. Our guest is sitting in position 2. So we have 2-bromopropan. In the second one, our guest in position 1. So we have 1-bromopropan. All of them have the same molecular formula. All of them are the same, but they are different in their position. Another example, we have chlorine. We have 2 chlorine atoms are attached to phenyl ring. They are attached to phenyl ring in different positions. In the first one, we have 2 substitution in position 1 and 2. 1 and 2 position are known as ortho position. So we have orthodichloropenicillin. In the second one, we have 2 chlorine atoms are attached in different positions, but our positions is 1, 2 is empty, 3 is empty, 4. So we have 1 and 4. So we can say we have para-dichloropenicillin. So they are just different in the positions, but exactly we have the same molecular formula. In the last example, we have chlorine atom attached to pentan, meth-eth-prop-but-pent. So we have 1-chloropentan. It is the first one. The second one is 2-chloropentan. So we have 2 compounds exactly with the same molecular formula, but they are different in the position of our guest. They are different in the position of substitution, or they are different in the position of their functional group. Let's start to transfer to the last type of isomerism, functional isomerism. In the case of functional isomerism, we have the same molecular formula, but we have different functional groups. I think you need to memorize the functional group. You will find it in the nomenclature of organic compounds. You will find the different types of functional groups in organic chemistry and how we can know each functional group. So we have different isomers have the same molecular formula, but they are different in their functional groups. Like, for example, in the first one, we have dimethyl ether. So our functional group is ether. In the second one, we have ethanol. Both of them have the same molecular formula, C2H6O. All of them have the same number of carbon atoms, 1, 2, 1, 2, and we have 6 hydrogen atoms and 1 oxygen atom. But we have different functional groups. We have different reactivity of the compounds. We have different types of chemical reaction related to our functional groups. In the first one, we have ether. In the second one, we have alcohol, ethanol. Another example, we have our aldehyde is our propionaldehyde. Our propionaldehyde is one of aldehydes, and our allyl alcohol. Allyl alcohol is another alcohol. Both of them have the same molecular formula like propylene oxide. They have the same molecular formula, but they are different in their functional group. We are transferring between different functional groups, between aldehydes and alcohols. Another type of, or another example of the functional isomerism is propanal and propanone. Propanal and propanone are different types of the functional isomerism. In the first one, we have aldehyde. Propanal, meaning we have aldehyde with CHO group. In the second one, we have ketone, acetone. Our functional group is just the carbonyl group C double bond O. So we have the same molecular formula, but we still have different functional groups. So it is the third type of the structural isomerism. Now we will transfer to one important topic, how we can calculate number of isomers. If we have alkanes and he starts to ask you to determine the number of the isomers of one compound, we will start to follow the following rules. At first, according to the number of carbon atoms in the compound, we will follow our rule. At first, number of carbon atoms is generating from 1 up to 7. We will follow the rule 2n minus 4 plus 1. 2 raised to the power n minus 4 plus 1. So by applying n is the number of carbon atoms. By applying the number of carbon atoms to 1 minus 4 plus 1, 2 minus 3 plus 1, 2 equal 0. 0 plus 1, so we have 1 isomer. In the case of 2 carbon atoms, 2n is 2 minus 4 equal minus 2. So we have 2 raised to the power minus, we expect it equal 0. 0 plus 1 equal 1. In the case of 3 carbon atoms, 2n is 3 minus 4 plus 1. 3 minus 4, we have 2 raised to the power minus 1. Minus 1, 2 raised to the power minus 1 equals 0. 0 plus 1, we have plus 1 isomer. We have 4 carbon atoms. 2 raised to the power n minus 4. 4 minus 4 equal 0. 2 raised to the power 0 plus 1. 2 raised to the power 0 is exactly 1. 1 plus 1 equal 2. So the number of isomers in the case of carbon atoms is 2. By transferring to the 5 carbon atoms, 5 minus 4 equal 1. 2 raised to the power 1 is 2. 2 plus 1 equal 3. In the case of 6 carbon atoms, 6 minus 4 equal 2. 2 raised to the power 2 equal 4. 4 plus 1 equal 5. In the case of 7 carbon atoms, 2 raised to the power 7 minus 4 equal 3. 2 raised to the power 3 equal 2 times 2 times 2 equal 8. 8 plus 1 equal 9. Let's start to have the shape of our isomers. At first, in the case of methane, we have one carbon atom. We have only one isomer, methane. In the second one, ethane, we have two carbon atoms. Number of isomers is 1, so we have only one isomer. In the case of propane, we have 3 carbon atoms. Number of isomers is still 1, so we have only one shape of propane. Let's transfer to the another isomers. In the case of butane, we have 2 raised to the power n minus 4 plus 1. 4 minus 4 equals 0. 2 raised to the power 0 equal 1. 1 plus 1 equal 2. So we have 2 isomers. At first we have N-butane. Its skeletal formula 1, 2, 3, 4. And its structural formula or displayed formula. In the case of isobutane, we can say in the case of 2-methyl propane, we have one branched isomer. We have one methyl group attached to our propane chain. In the case of pentane, our carbon chain will increase to 5 carbon atoms and our isomers will increase to 3 isomers. 1, 2, 3. First one in pentane, second one isopentane, third one is 2 and 2 dimethyl propane. It is new pentane. So we are transferring in chain isomerism. It is a chain isomerism. The length of our carbon chain is changed from 5 carbon atoms 1, 2, 3, 4, 5 to 4 carbon atoms and 2, 3 carbon atoms in new pentane. In the second one, we have hexane. In the case of hexane, we said we have 5 isomers. In the case of hexane, we have 5 isomers. The first one is normal hexane. Second one, 2-methyl pentane. We have branched compound. And we have 3-methyl pentane. The relation between 2-methyl pentane and 3-methyl pentane is positional isomerism. We have just methyl groups. They are different in their position, just in their position. But in relation between our normal hexane, we have chain isomerism. We have different shapes of isomers. They are different in their length of carbon chain. We have 2 and 3 diethylbutane. Take care in naming. We are transferring meth, eth, prop, but. So we have 2-methyl and 3-methylbutane. We are looking for the longest carbon chain in our compound. We have 2 and 2 dimethylbutane. 2 and 2 dimethylbutane, meth, eth, prop, but. We have 2 branches. We have 2 guests on carbon atom number 2. So we have 2 and 2 dimethylbutane. They are the 5 shapes of our isomers in the case of hexane. Let's complete in our rule. At first, if we have 8 carbon atoms, our rule will change it to n raised to the power n minus 4 plus 2. So the number of isomers will be 18. Just calculate it. 2, 8 minus 4, 2 raised to the power 4. 2 raised to the power 4 equals 16. 16 plus 2 equals 18. 9 carbon atoms, 2 raised to the power n minus 4 plus 3. So 9 minus 4 equals 5. 2 raised to the power 5 equals 32. 32 plus 3 equals 35. In the case of 10 carbon atoms, 2 raised to the power n minus 4 plus 11 equals 75. Now we will start to show the different shapes of heptane isomers. In the case of heptane isomers, we know that our number of isomers will be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we start with normal heptane. We start with withdrawing one carbon atom from the long chain and start to transfer it in the positions in our chain. So we have hexane with one branch with methyl group. Our branch can be in position 2 or position 3. So we have two isomers. We have two positional isomers in the case of methyl hexane. Then we will start to transfer two methyl groups. So we have pentane, but with two methyl groups are changing in their position. The probability for changing the position of our methyl group will give us different types of isomers, as 2 and 2 dimethyl pentane, 2 and 3 dimethyl pentane, 2 and 1, 2, 3, 4, 2 and 4 dimethyl pentane. We start also to transfer our methyl group with 3 and 3 dimethyl pentane and the 3-ethyl pentane. At last we transfer 3 methyl groups, so we have 2, 2 and 3 trimethyl methylpropbutane. We have 3 and 3, 2, 2 and 3 trimethyl butane. So they are the different types of isomers in the case of heptane. And our rule is 2n minus 4 plus 1 from 1 up to 7 carbon atoms. At 8 carbon atom, 2n minus 4 plus 2. At 9 carbon atoms, 2n minus 4 plus 3. At 10 carbon atoms, 2n minus 4 plus 11. At last, I have one important information. Please take care of it. As the number of carbon branches increase in our molecule, the boiling point and melting point of the compound will decrease. Why the boiling point and melting point will decrease? Because the number of intermolecular force of attraction, the number of intermolecular force of attraction, van der Waals force of attraction will decrease. As the number of intermolecular force of attraction will decrease, be sure that the boiling point and melting point of your compound will decrease. So, for example, if we have pentane in straight chain, we have 5 carbon atoms are arranged in a straight carbon chain. They can form equal number of van der Waals force of attraction. It can form the largest number of intermolecular force of attraction, van der Waals force of attraction, between the 5 carbon atoms. So we have very large number of van der Waals force of attraction. We have large number of intermolecular force of attraction. So its boiling point and melting point will be high. But in the case of our branch compound, in the case of another isomer, in the case of another chain isomer, 2 and 2 dimethyl propane, exactly we have the same molecular formula, C5H12, but we have different isomers. The first isomer is straight chain, the second isomer is branched chain. 2 and 2-dimethylpropane. We still have number of van der Waals force of attraction, but our number of van der Waals force of attraction decreased. We have large number of force of attraction 1, 2, 3, 4, 5, 6, 7, 8, 9, but we have only one van der Waals force of attraction. So the number of forces of attraction will decrease as the number of branches will increase. As the number of forces of attraction decreased, be sure that the boiling point and melting point of your compound will decrease. So the boiling point of our compound is 9.5, but the boiling point of a straight chain is 31.6 Celsius. It is very important point to take care of it. At last, thanks for watching our video. Wait another video for stereoisomerism, inshallah. And don't forget to make share and like to our video and share it with your friends. And don't forget to make subscribe to have any new video. Thanks for watching. See you later. Assalamu alaikum wa rahmatullahi wa barakatuh.